welcome to the course Advanced Reaction Engineering. So, already we have started the bioreactors and bioreactions from cell to more cell formations or new product formations. Means if we any bioreactions conduct in any bioreactor, so then we have to supply the substrate as well as new cell, and with that we will get more cells as well as new product formations would be there, that already we have discussed. So, today we will discuss about 1-2 examples, means numerical problems we will discuss related to the bioreactions, and at the same times means yield coefficient determinations and rate law parameter estimations that we will discuss. So, in the bioreactors this is the cell reactions, means inside of a cell, inside of a bioreactors there is a cell and substrate that we usually take for the reactions, and we maintain a particular temperature, pressures, nutrients, everything we maintain. So, then cell reactions will take place and more cell formations would be there. At the same time product formations is there, that product is useful or valuable product is there. So, that is why we usually conduct any bioreactions in a bioreactors. So, these reactions we can write this way also, means substrate that would be converted into new cell as well as product. So, the cells initially we have started with very small amount of the cells or microorganisms or bacteria that we have taken. Basically, that cell culture would be there inside of the reactor, that substrate would be converted into corresponding new cell. At the same times product formations is there. So, if it is possible to sort out the substrate that is consumed in presence of cells to form new cells, from that substrate it is consumed and to form the product. So, it is that is our curiosity, means we want to know, means whenever we are going to study, means how much amount of the substrate that is being consumed by the cells, means that amount of the substrate being consumed by the cells to form the products. So, for that we need already have discussed what is called yield coefficients, that is basically relative weight ratio with respect to the means one component. If we want to know, means how much concentrations or weight of that particular component is being formed, and with respect to the other components. See here components are substrate, cells and products, these are the three components are there. So, then see here y prime C is, that is the mass of the substrate that is consumed to form new cells per mass of the new cells formed, means here new cell formed, here substrate is consumed. So, here substrate consumption with respect to the new cell formations we are expressing in this way, y prime C by S. Similarly, with respect to the product formations and substrate consumptions, if we express this way also, mass of the substrate that is consumed to form product per mass of the product form. Okay. So, here this way also we can write, and some other form also we can write, that already have discussed in your previous class too. Again I am just repeating that part. So, mostly whenever any cell reactions is going on, so all that also we have discussed, that substrate utilizations, means what are the way that substrate we are putting inside of the reactors that is being consumed. That substrate basically consumed three way, one is the more cell formations, number of product formations and cell maintenance. These are the three way that substrate being consumed. Okay. So, whenever substrate concentrations or disappearance of the substrate in the cell reactions if you want to know, then rate of substrate disappearance minus RS, as that way S means substrate and minus R means disappearance or consumptions of that rate of consumption of the substrate. So, that three way, new cell formations, product formations and cell maintenance, if we sum up these three ways substrate being consumed. So, here rate of cell formations, new cell formations, Rg is the rate of cell formations and y prime S by C, that is the yield of the cells per unit of the substrate. Similarly, product formations, rate of product formations, yield of the product per unit substrate consumptions. Similarly, for cell maintenance, so the amount of the substrate being consumed, that we can put it here. That way these equations we can use to know the how much quantity of the substrate being used for the total means new cell growth or new cell formations, product formations as well as cell maintenance. Okay. So, here in these equations here this is the in general substrate utilizations for any cell reactions. So, whenever this type of means graph we have discussed here, the means from the beginning to the here x axis is the time. So, here t equals to 0 time to t equals to t times. So, this is the 0 time. So, this is the pathway means from initial means when we have started the reaction of the cell reactions in presence of substrate, and finally the time is passing by these different phases, and then the overall means bioreactions reactions is completed. So, this is the lag phase, this is the growth phase. So, and this is the stationary phase. So, growth phase I said, if there is in the growth phase what happens, the substrate consumptions is there, but the new cell formations is there. So, this is the growth phase, and in the stationary phase there is no cell for new cell formations. Whatever the cell formation is there in this stage, that same concentration remain there, but only new product formations might be there at this stage, means cells means substrate converted into the new product formation. So, product formations is there, here there is no cell new cell formations, here new cell formation is there. So, and after that means cell gradually dies or death rate is there. So, here if we look into this particular phase, phase 2, so there's this is the general substrate consumptions or disappearance reactions we can write. So, at this stage if we say that at stage 2, this is the case ones we are discussing when use of the substrate growth associated with the product formations. So, this is means if there is no product formations at stage 2, only new cell formations is there. So, then these equations we can write, these equations, this part in these equations we can eliminate, only this part and this part is left. So, then these equations we can write this way. Okay. So, here's means rate of substrate consumptions, that is due to the new cell formation as well as cell maintenance. So, that is the growth associated with the product formations. In growth phase means the substrate consumptions is there, if any product formations is there at this stage. So, this way also we can find out how much concentration of the substrate being consumed at this particular stage in the growth phase. Number 2 is the case 2 is secondary non-growth associated product formations at this stage. So, in the stationary phase what is happens, new cell formation is not there, only product formations is there. If there is any substrate consumption, that is for due to the cell maintenance as well as product formations. Okay. So, usually this is the non-growth associated, non-growth means no cell formations, okay, only product formations is there at this stationary phase. So, in this particular phase 3, so we can write the mono equations this way, Rp equals to Kp Csn Cc by Ksn plus Csn. So, here Kp is the specific rate constant with respect to the product, Csn is the concentration of the nutrient that is or substrate that is being consumed, and Cc is the cell concentrations, and Ksn is the Monod constant, and Rp is the rate of product formations. So, rate of product formations at this stage is there, at stationary phase product formation is there. So, how much product is formation is there per unit times, if you want to know this type of Monod equations you have to use, that is at similar to the cell growth rate equation, similar type of equations. Okay. So, for this particular, see here this equation, this is the general substrate consumptions equations. So, in this equations you can see minus Rs, that is the rate of substrate disappearance due to the 3 reasons, means cell growth, this is the cell growth or new cell formations, product formations and cell maintenance. So, here stationary phase or this phase stage 3, here there is no cell formation, therefore, this part we can eliminate. So, remaining these are the 2 components, means cell product formation as well as cell maintenance, that is the 2 reason for that substrate that was present inside of the reactor being consumed. So, therefore, these equations we can write this way. not this way we can write. Okay. So, minus R s equals to Y S C R G plus M C C. So, this is for cell maintenance substrate consumption, and this is these equations we can write in this way. This way we can write here in terms of the product. Okay. So, similar type of equations we can write. So, equations these equations means minus R S N, that is the rate of substrate consumptions, equals to rate of product formations, rate of cell maintenance, the amount of the substrate being consumed. So, here R P is this equation actually for cell growth, means that we have written here, that is rate of formation of the cells. In place of that we are writing rate of product formations. Similar type of equations we are writing, and this is the yield coefficient also with respect to the product and substrate. So, we are writing here. So, this is the equations we have to use when at for stationary phase product formations and cell consumptions or substrate consumptions. So, these equations we can write MCC, that is for cell maintenance substrate consumptions, and this is for rate of product formations, the substrate being consumed. Okay. So, these equations we can write. So, here this is for the stationary phase, rate of the substrate disappearance at the stationary phase is due to the cell maintenance, and this is the due to the product formation. So, if we solve these equations, then we can find out for the stationary phase how much quantity of the substrate being consumed for that particular stages. Okay. And this is the rate of product formation Monod equation that we know, that we have discussed. So, similarly or other way also neglecting cell maintenance. So, the rate of product formations or concentrations we can write this way also, concentration of the product, yield coefficient and substrate consumptions if you know, then that way also concentration of the product present, that way we can write. So, here two cases we have discussed. So, product at this particular stage growth phase, there only substrate consumptions is there, here is also substrate consumptions is there, but here new cell formation is there and here product formation is there. So, product formations only during the stationary phase and product formations is only during the growth phase. So, product may form here, product may form here. These are the cases in bioreactions, possibilities there, either these phases or growth phase with the new cell formations, product formations might be possibilities there, case is 1, and case 2 is the in the stationary phase, here there is no product formations, only product formations would be the stationary phase. This is the two cases. There is another cases or the exceptional cases that we can say. So, when means substrate that is being converted into the product. So, in the growth phase also product formation is there, stationary phase is there, there also product formations is there, means product not only here product will form, product also may form here also. So, here maybe with the cell formations product formations is there, but the rate of product formations is slow, less than this, maybe or maybe high. So, this is the exceptional cases or third cases. These two cases means other than these two cases there is another cases is there, in that case here also product formation is there, here also product formation is there. So, in that case the Monod equations or the equations that you have to use to find out the rate of product formations or the rate of substrate disappearance if you want to know, this Ludeking-Piret equations you can say, these equations we have to use. So, here's Q P, that is the rate of product formations, this is due to the cell growth or cell formations, and at the same times that is the non-growth which is due to the, we can say only that is the non-growth phase. So, here we can say this is the growth phase, this is non-growth phase. So, this is the secondary nutrients or excess nutrients that is in excess, means here specific growth rate, and here's at this particular phase how much quantity of the substrate being consumed at this particular means phases or stationary phase, how much concentration of the substrate being consumed to form the product. So, two cases substrate consumptions is there, if we sum of then total rate of product formations, means here substrate consumption is there as well as product formations is there, here also product formation is there. So, P1 P2 let us say. So, at this particular stage P1 quantity of product formation is there, at this particular phases or stages stationary phase P2 amount of product formation is there. So, then for this particular reactions or reactions, so total product formations would be P equals to P1 plus P2. Okay. So, this way you can define. So, here we have defined QP, that is the these parameters, rate of product formations. RP we can write if we multiply it with the concentration of the cells, QP equals to this, and then RP, rate of product formations, equals to QP multiplied with CC. CC is the cell concentration. So, here you can see by substituting this QP here. So, we can write RP equals to alpha mu g Cc plus beta into Cc. So, here means this is at this particular stage, means that is the growth phase. This particular is the growth phase, means phase 2, and this particular is for stationary phase. So, if we both sum up, then rate of product formations QP equal to, that is the mass of product per unit volume per unit times QP actually. So, if you multiply it with the Cc concentration, means substrate concentrations, then rate of product formations we can find out, that is gram or kg of particular product per unit times how much that is forms, that we can find out. Okay. So, these equations we have to use to find out the rate of product formations. So, we know means what are the different equations we have to use to find out rate of product formations, rate of cell formations, or rate of substrate disappearance for a cell reactions. Now, there is one examples to find out yield coefficients, means YSC, YCS, YSP, YPC, means with respect to the one particular yield of the product. Let us say substrate and cell reactions, substrate plus cells to new cell plus product formations is there. So, if we substrate consumption per unit cell, or substrate consumption per new cell formations, or substrate consumption per unit product formations. So, ratio of two weight means component yield, means how much this is actually yield, means ratio of two different components in terms of the gram. So, that we can write and these are the components already have discussed. So, what is the definition of the yield coefficient? So, these are the components we will find out. At the same times we know the rate law parameters. So, rate law coefficient mu max and Ks also we will find out by considering one simple cell reactions. So, here you can see this is the glucose plus cell if you take in a inside of a bioreactor. So, new cell formations would be theirs, and ethanol, that is the product, means glucose to ethanol conversions. If we have to use Saccharomyces cerevisiae, this cells you have to use. So, then more cell formation is there, and that glucose will be converted into the product, that is the ethanols. So, if we the experimental data is given here for this particular reactions, when time t equals to 0 hour, the new cell formation or cell concentration was 1 gram per dm³, and glucose, that is the substrate concentration, that was initially 250 gram per dm³, and ethanol productions at the beginning was 0. There was no product formation is there, so only new cell was that was put here, and the substrate initially that we have taken, so that is the glucose is this. So, once time is gradually increase 0 hour to 3 hours, the cell concentration C gradually will increase, and the glucose, that is the substrate concentration, gradually decrease, means substrate that is converted to form new cell formations, or new cells concentration gradually increase. Similarly, product formations also gradually will increase with increasing the time. If we increase the time, the new cell formations as well as cell concentration as well as product concentration, this is the product, okay. Concentration gradually increase. Only substrate concentration, this is the substrate concentration gradually decrease. So, this is the experimental data for this particular reactions. Now, we have to find out yield coefficient and rate law parameters we have to use. So, that how we can do. So, here these are the equations we have to use. This is the rate equations, rate of formation of the cells per unit times, this is the monod equations, and for the batch process or rate, we can rate of formation of the cells Rg equals to dCc by dt, that way you can write. So, here in the experiment, the experimental data is given. So, you can plot time versus concentration of the cells. X axis is the time and y axis is the cell concentrations. Okay, cell concentration initially was low, and with increasing time the cell concentration gradually increase. Similarly, product concentration was initially 0, so it gradually increase product concentration, and substrate concentration you can see this is the substrate concentration. It was initially 250, it gradually decreased with increasing time. So, this is the way, means the table signifies this. So, these are the equations we have, Monod equations, or these equations rate in terms of dCc by dt we have. Now, we have to find out yield. Okay. So, yield definitions also we have discussed for the cell reactions. YCS equals to this delta minus delta Cc by delta Cs, and YPC, that is the mass of product forms per mass of the new cell forms, and mass of product form per unit substrate consumptions. That way we can write. So, this is the definition of the yield, okay, individual components, and how they are indicate. So, here you can see, or in the table also it is given. So, in that next step, so we have to find out these are the components. Okay, that is very simple. So, in the experimental data you can see. So, these are the experimental data for 0 hour, 0 to 1 hour. If you see 0 hour and 1 hours, these are the data we have. So, YSC equals to minus delta Cs by delta Cc. So, here minus is there, delta Cs equals to the substrate change concentration. This is the substrate 250 to 245, and concentration of the cells 1 to 1.37. So, that way you can write. So, YSC, that is the yield of the substrate per unit cells, equals to 13.51 gram substrate, that is consumed per gram of the cells. Okay. Similarly, for 2 hours to 3 hours, that period of times cell changes and substrate changes we can know, and then YSC for this particular time range also we can find out that much. Okay. So, now we are taking average. So, YSC, that is equals to 0 to 1 hours, and 2 to 3 hours is this average if we take. So, then 13.3 gram of substrate per unit cell formation, or per gram of the cell formation. So, this is the yield coefficient for substrate and cell. So, similarly, YCS also we can write this way inverse, that is that much gram of cells that is being formed if per gram of the substrate consumptions is there. So, this is just inverse of this. Okay. So, this way we can write, or we can interchange with each others. Similarly, we can calculate the substrate and product yield coefficients YSP or YPS we can find out. So, YSP similarly this is the definition. So, minus delta Cs by delta Cp. So, if we put these are the components value, so then it is coming this. So, these are the value we are putting from the table. Okay. So, 1 hour to 2 hours. So, 1 hour to 2 hours 245, that is the substrate initially 1 hour, that was 245, and 2 hours 238.7, and corresponding product that was 2.14 and 5.03. So, based on that, the amount of the substrate being consumed for per gram of the product formations, or yield coefficient YSP we can find out this, or YPS also we can write by that is just inverse, means per gram substrate how much product we can get. So, this way we can also interchange with each other from one yield coefficient to another yield coefficient. So, next is the for product and sales yield coefficients. If you want to find out for between time 1 to 2 hours, if we compare 1 hour to 2 hours. So, within that cell and product, this is the product and this is the cell. So, these are the components we have to use to find out YP by C. So, yield coefficient for product per unit of cell. So, that much of if we put these are the components here in this equation. So, then 5.78 gram of product form per gram of cell. Okay. So, similarly, here also YCP also we can find out, that is that much gram of the cells per gram of the products, means if there is 1 gram of product form is forms, with that much gram of the cells formations is there. Okay. So, now we have to find out the rate law parameters from the Monod equations. So, Ks and mu max that we have to find out. So, that is the definition of rate, Rg equals to Cc by dt, means rate of cell formations per unit times we can write Rg, rate of cell formations, and Monod equations equals to this, Rg equals to mu max Cc Cs by Ks plus Cs. Ks is the rate law parameters and mu max is the rate law parameter. These are the components unknown parameters we have to find out. So, here this monod equations is theirs, we just rearranging these equations or we are writing this way, just inversing this. So, if we rearrange these equations we can write this way, left hand side this, right hand side this and right hand side is this. Okay. So, here substrate concentration is given, that is the substrate concentrations, and concentration of the cell concentration is also given. From the experiment we can find out, these are the two components, and Rg, that is we do not know, but from this experimental data we can find out Rg equals to dC C by dt, that is equals to Rg, rate of cell formations that we can find out. So, using times, and these are the two data with the cell concentration at time, this data we can use to find out this. How to find out this, that we will discuss, to how to find out Rg value. Okay. So, first what we have to do, so these are the components we have to plot cell concentration y axis and time time x axis and cell concentration in y axis. So, these are the plots will come. So, this is the means this type of plots will comes. After that we will do the polynomial fit. Okay. So, once we do the polynomial fits, so then concentrations and times, this type of equation or concentration as a function of times will come. Okay. So, if we differentiate this, so then it would come this. Okay. After differentiation with respect to the time, if we do, then dCc by dt will come. So, this is equals to rate, okay, at as a function of times. So, here's what we have to do, time equals to 0, 1, 2, 3 hours. If we put corresponding Rg value we can find out. Okay. So, this is the way to find out rate of generations of new cell formations that we can, by using polynomial fit, graphically we can find out. Okay. So, by polynomial fits we are getting, means initially experimental data was given this, after that individual times Rg value we can find out, 0 hours, 1 hour, 2 hour, 3 hour we can find out. Then once Rg value is known, then Cc by Rg we can find out, Cc is given, Rg value is known, then Cc by Rg individual times we can find out, and Cs is given, that is the substrate concentration, 1 by Cs we can find out. Okay. Just inverse of this, Cs 1 by Cs, Cs is given 250. So, 1 by 250, that way what are the value would come, that is the first value. So, like that 1 by Cs value we can find out. Okay. So, in these equations left hand side and these components is present. Okay. So, this is, and this is we plot in y axis, this is x axis we will plot. Okay. So, now if we plot this, so in the y axis Cc by Rg and x axis 1 by Cs we are plotting. So, these lines will come like this. Okay. So, what are the value is coming by considering this value of this column. So, if we plot, then the lines will come like this. So, here this is called intercept and this is the slope. Okay. So, slope and intercept for these lines from this graph we can find out, from these graphs we can find out slope, some numerical value would come. Okay. That may be 0.5, 0.3 whatever. So, then Ks by mu max we can find out, and from the intercept also some numerical value we can find out. So, from here mu max we can find out. So, mu max we can substitute here, then Ks we can find out. So, by from this graph mu max is this for this particular reactions and Ks equals to this. So, from the polymath nonlinear regressions we can find out mu max in the monod equations. You can see in that monod equation, this was the monod equations, rate of cell formation, that is equals to mu max rate law parameters plus Ks, that is the unknown parameter that we can find out once we have the experimental data. Here substrate concentration and cell concentration, that is the from the experiment we have to find out, and what are the value will come mu max and Ks that we can put, then corresponding the final equations Rg equals to we can write mu max 0.33, Cc Cs by Ks equals to 1.7 plus Cc. Okay. So, this is the rate equations or for the rate law for this particular reaction. So, what was the reaction? So, that reactions was for this particular reactions means yield coefficients we have derived or we have find out for this particular once the experimental data is given, and rate law parameters from the Monod equations we also find out by using the polynomial fits we can find out a rate and corresponding rate law coefficient or rate law parameters we can find out. Okay. So, these are the way we can find out means first this graph 1 to graph 1 for to find out rate, and this is graph 2 that is for rate law parameters to find out means slope and intercept we have to find out, then mu max and Ks that is the Monod equations constant that we can find out. So, this is for one examples I have shown and discussed. So, similarly for other cell reactions also if we are able to find out these are the experimental data means with changes of the times cell concentration changes, substrate concentration changes and the product concentration changes, if we are able to identify and quantify, then Monod equations we can means solve for this particular reactions or particular equations yield coefficients also we can find out. Okay. So, so today is up to this. Thank you.